Well, hello again. In this example, you examine the method of sections to find bar forces in a parallel chord truss. Here is the truss we will be examining, and we're being asked to identify the internal forces in members CD, CM, and LM. But to further enhance the experience, we are also asking that equilibrium equations are written so that they are only in terms of one unknown force. We want to avoid simultaneous equations if at all possible. Now, the advantage of the method of sections is that we can get right to the members of interest, and I can make a cut through my truss, which happens to intersect all three members of interest right here. At this stage, you can either use the left-hand side of the truss or the right-hand side of the truss after making the cut. Please be aware that for the inclined members, we've identified its components for vertical and horizontal there. So since it becomes a little bit cleaner and easier, I'm going to use the left section for my free body diagram. Recognize we've got the vertical reaction right here, and we've got the vertical forces of 4 kips at joints B and C. So what we want to do is complete the free body diagram by sketching in my unknown bar forces. Got N, L, M down here. And the only bar that has multiple components is bar CM. So we'll go ahead and get horizontal and vertical components, always assuming positive. That means pointed out from the member. This will be 1 over square root of 2 NCM. And the vertical component will also be 1 over square root of 2 NCM. We are going to need to have this piece of information here if you hadn't picked it up on the first diagram that was given to you. That is 12 feet tall. Now what we want to do is look for an equilibrium equation that contains only one unknown. There is an obvious one we can start with, and that is some forces in the y direction. This will give us 14 kips minus 4 kips minus 4 kips minus 1 over the square root of 2 NCM, and that will be equal to 0. So NCM is equal to 849 kips, and since it worked out to be a positive value, we do know that it is in tension. That's the advantage of always assuming all your bar forces to be in tension. Now the next equation of equilibrium we could try is by summing moments about point C. You will notice if you look at point C that bars CD and CM act through that, so the only unknown we would have is NLM. Let's go ahead and get that equation of equilibrium written. So sum of moments about point C. This will equal to negative 14 kips times 24 feet plus 4 kips times 12 feet plus NLM times its moment arm of 12 feet, and that will be equal to 0, and thus we can explicitly solve for NLM at being 24 kips. That is a positive value, which then means that that bar is in tension. At this stage, there are a number of different equations of equilibrium that you could use to solve for the remaining unknown. But we want to go ahead and use one that does not rely upon us knowing or having gotten correct any of the two previous answers. And so what we're going to do is we're going to sum moments about point M. And I want you to notice if I project this line out here, point M is right out here. So we don't have to be summing moments about a point that is on the free body diagram. We can do it anywhere that is convenient to us. And thus we can write an equation of equilibrium that is only in terms of member CD. So let's go ahead and get that one taken care of. We'll sum moments about point M. Here's our positive sign convention for that. And we get a negative 14 kips times 36 feet plus 4 kips times 24 feet plus 4 kips times 12 feet minus NCD times 12 feet, and that is all equal to 0, and thus we compute NCD is equal to negative 30 kips, and the negative indicates to us that that bar is in compression. It's as simple as that, and that concludes our example. And as always, it is a beautiful day to study structure.